Hello, and welcome to the latest ICCT webinar, Transitioning to Alternative Vehicles and Fuels, a Vehicle Technology Assessment in the NAS Report. I'm Joe Schultz. I'm the Communications Director of the ICCT. In a minute, I'll hand it over to John German, our presenter, and Anoop Banavadekar, our Passenger Vehicles Team Lead, who is also present and will be helping out with the webinar. But first, a couple of housekeeping details. During the presentation, we will keep everyone in listen-only mode. That's strictly a measure to preserve audio quality over the internet. If you have any questions during the presentation, which we expect will last about 45 minutes, feel free to type them in using the question pane in your control panel. Anoop will be paying attention to that, and he can either respond or maybe queue them up for discussion later. Following the presentation, we'll open the floor for questions and discussion. In order to kind of manage that process, Anoop will be kind of the master of ceremonies, and if you'd like to ask a question via the audio during that part of the webinar, just raise your hand. Use the icon up in your control panel to raise your hand and let Anoop know that you'd like to be unmuted and ask a question. And we will have about half an hour, 45 minutes we expect for discussion following the presentation. Just a reminder that this is being recorded as well, so it'll be available on our website after once the recording is ready. So with that, let me turn it over to John German, our senior fellow, and we'll get started. John?
Yes, hi, welcome everybody. I'm going to start off by giving okay, Joe, it's not letting me advance these slides. So hang on a second, folks, and let's see if I can fix this or not. There we go. Okay. I was on the National Academy of Science Committee on looking at transitions. We were looking at 2050. I'm going to start off with a few slides summarizing the overall report, task, and findings. And once again, I'm having problems. There we go. Statement of task. And the baseline we were assigned was 2005. And the task was to look at petroleum use, 50% reductions by 2030, 80% by 2050, and greenhouse gas emissions, 80% by 2050. Looking at the performance of the vehicles, the options, the cost, barriers hinder the adoption. And another major part of it was to suggest policies to help achieve the goals and a comment on what kind of R&D programs would be helpful in meeting the goals. There were 4 pathways that we examined: internal combustion vehicles, which in this case includes hybrids, biofuels, electricity, and hydrogen. We also looked at natural gas, but we concluded that while they can be very effective to help reduce petroleum consumption, they're not likely to have much impact on greenhouse gas emissions. And this is because methane is such a potent greenhouse gas that only a small amount of leakage will offset the CO2 benefits. And the other thing that was evaluated by a fuels group was to look at how these alternative fuels are being created, and it has a major impact on the greenhouse gas benefits. Key findings: we didn't find a single pathway which would be, by itself, could meet these 80% reduction goals. At least 2 and maybe more will be needed. The improved efficiency across all the types is essential. The goals can be met. It'd be very difficult, but they're not impossible if they're supported by strong national policies. And I think a real key finding is that, of course, even if the goals aren't met, you can still have considerable valuable benefits from this. Policy side, you have to have strong and effective policies, or you're not going to get anywhere close to the goals. And you have to drive the advancement of technology in both fuel economy and reducing greenhouse gas emissions. One, of course, the problems we've had in the past is these technologies being used to improve performance instead of efficiency. And you must transform the fuel infrastructure if you're going to meet the greenhouse gas goals. There's a lot of uncertainty about which of these technologies is going to succeed, and therefore the policies have to be flexible, broad, and adaptive so that they can change and adapt as technologies advance. So that's my real quick overview. If you want to look at the full report, web link is on here. Now I'm going to turn to talking about vehicles. The committee did much of its work in 3 subcommittees, one on vehicles, one on fuels, and one on modeling. I was the head of the vehicles subcommittee, and that's what I'm going to talk about here. I'll take a deep dive into this. Now, I'm also aware that we have a lot of different types of people on the phone. And so for the gearheads, I am going to get into some of the details of what we did, but I will spend most of my time just talking more about the overview of how we went about things. So I have a lot of very detailed slides with lots of numbers on them, but I'm going to go through those very quickly and just try to highlight a couple of major points. Okay, so with all that as background, we'll start talking about the vehicle technology assessment that was done. And the key point here is that when we looked into existing sources of information, we really didn't find anything existing that was really adequate for 2050. People have looked at 2050, but it tends to be someone assessed a battery electric and somebody assessed a different type of vehicle, and they were not done in a consistent way. So we decided early on in the process that we needed to create our own techniques, and that's what I'll be talking about here. So everything I'm going to show you assumes that aggressive policies exist that are going to drive the development and the implementation. So this is an assessment of what is possible and feasible, assuming the policies are in place. We assess 2 different pathways. One is our mid-range case, which is our best assessment, should all technologies be pursued vigorously. And then we had a stretch case, which we call the optimistic case. But we still consider this to be quite feasible. It's just more things work out. The primary thing that we did is we tried to make sure that we applied consistent assumptions everywhere. So, for example, our load reductions were applied equally to all of the different vehicle types we looked at. And then when we did cost assessments, we tried to build up from one vehicle type to the next. I'll talk a lot more about these things. The other problem we had is that if you're looking at especially engines, these have tended to be modeled in the past by looking at discrete technologies and what the efficiency is of each discrete technology. This doesn't really work for 2050. Nobody knows what the technologies are going to be beyond 2030. So what we did is we adopted an approach where we assessed the system efficiencies and losses, not individual technologies. And I'll talk more about that too. So this is kind of a flow chart for how we assess the efficiency side. I'll talk about cost later. So for the efficiency side, we started for ICEs and hybrids, we started with some simulations that Ricardo did for the 2025 rulemaking under contract to EPA. From these, it flows to EPA created what they called energy audit from the Ricardo simulations, where they collected the results in the simulations into discrete categories of losses and efficiencies. And then so on the flow chart here, we can go, so these all feed into the baseline losses from the baseline data. And then there's also a 2025 case, which fed into 2030. For our mid-range assumptions, we took the Ricardo 2025 simulations and applied them to 2030, under the assumption that it would take until 2030 for these technologies to be spread across all vehicles. And then it was also, Ricardo did a hybrid simulations which fed into 2030 hybrid losses. The base vehicles were taken from the Ricardo, or soon to be the same as Ricardo. Ricardo did not do load reductions. These were assessed separately by the committee, and then all these things wind up feeding into an energy balance model. This is a model from Dan Mesler, Mesler Engineering. And from this, we got calculated the ICE and hybrid efficiencies. Now that's kind of the first step. As we also put in more inputs for 2050, these also got fed into the energy balance model as well. The other key output from the energy balance model was the amount of power needed to maintain constant performance. This is a key input into the cost calculations. So talk a little more about each of the pieces. The Ricardo technology simulation modeling was the basis for much of the standards that were set for 2025 by EPA and NHTSA. They modeled 7 vehicle classes. We used 6 of the 7. We did not do the heavy light duty truck, but the first 6 on here we assessed as part of our work. They also did this over a number of drive cycles. We used only the FDP in the highway because we were just looking at fuel economy. They also modeled a number of different types of technologies. The first table is the engine technologies. They had a baseline, and then they had 5 different gasoline technologies and 1 diesel. So I have outlined in red the specific technologies that the NES committee used for our assessments. So of course the baseline, and then we elected to go with a boosted EGR, direct injection engine. The efficiency wasn't quite as good as the lean stoic DI turbo, but we thought that because of emission considerations, it was a more reasonable choice to start with. Ricardo also modeled 3 different types of hybrid configurations, and we chose the P2 parallel. This is a hybrid with a single small electric motor and 2 clutches, 1 on each side of the electric motor. It provides most, if not all, the benefits of the power split system, and it is lower cost. It's also what EPA selected for their rulemaking. And then finally on the bottom is some transmission technologies. We used the DCT, although it varied from the dry clutch DCT for the smaller vehicles to the wet clutch for the larger light trucks. Now when Ricardo does its simulations, it's based on a combination of maps of things like engine efficiency and motor efficiency, and then calibration strategies so that it actually does a virtual shifting and running of the engine over a test cycle. So this is an example of one of the types of engine maps that they use in their modeling. On the y-axis is engine torque, on the x-axis is engine RPM, and then these are lines of BSFC, brake-specific fuel consumption, in grams of fuel per kilowatt. And you can see these is where the highest efficiency is, and then the fuel consumption goes up as you come away. So this is the map that Ricardo has generated based upon their own internal data. For comparison, the one on the right is a map from a 2011 General Motors paper, and if you go through them, they actually show a pretty good agreement. Another example of a map, this time for an electric motor. Again, a speed on the X, torque on the Y, and these are efficiencies. So the electric motor, this baseline electric motor was 92% efficient in the middle, and it does fall off somewhat as you go to higher speeds and lower torque. Although it's still, the fall off is not nearly as great as it is on engine efficiency. Some reason to believe that Ricardo may have been conservative in their assessments. This is one example here. We chose the boosted EGR version of the engine. This is Ricardo's map that they used for boosted EGR. On the right is a map that was published 3 years ago and from the HEDGE Consortium, which is being run by Southwest Research. This was the HEDGE Consortium's first concept with a single stage turbocharger. And you can see that if you look at the best fuel consumption for Ricardo was 225 grams, and for the Hedge it was significantly lower at 216 grams. Now the Hedge does fall off faster as you move away from that best point, but still overall it appears that the map that Ricardo used was not as good as this 2010 concept, and Southwest is already, in the Hedge consortium, are already moving on to more advanced concepts with even better fuel consumption. Okay, next step. The outputs from the Ricardo simulation model went through, EPA created an energy audit data so that they could see how the technologies are being broken out into different types of losses. I'm not going to go through this slide. I'm just showing you, putting it up to show some of the detailed information that EPA summarized from the Ricardo simulations. So for engine, you have about 12 different characteristics: transmission, time and gear, efficiencies, battery characteristics, MG1, that's motor 1 or motor generator 1 and motor generator 2. What I'm going to concentrate on is the energy distributions. So the first column here, these are all in kilowatt hours. The first column is the total fuel energy. And this is exactly matches the fuel consumption of the vehicle. It's just the inverse. And then from this, they broke it down into a number of different energies and losses. So for example, you have engine pumping losses, engine friction losses, the indicated energy, which is related to the indicated efficiency of the engine. You have accessory losses, losses to the brakes, and that leads you to a net brake thermal energy. You also have losses in the torque converter, the transmission, battery loops, power electronics, motor generators. This particular chart is just for an ICE, so those are 0. Total driveline losses, then you have the tractive energy losses to aerodynamic drag and tire rolling resistance, and so on. So these breakdowns are not perfectly accurate. EPA is having to make some estimates as to how they put some in these categories. But they've done some double checking of these, and the estimates are pretty good. And the other thing that is, but the biggest reason that we use this is that we know that all of the losses sum properly. There are certain things in here that are directly measured on the cycle, such as the total fuel energy. So even though it might have a few losses assigned inappropriately, we know the total sums. This is the same, except now we're looking at for the hybrids. Now you have inputs for some of the battery loop losses and the motor losses. EPA also had to put in some additional detail about just how energy flows through the hybrid system in order to get all these energies to work out right. So you have engine power to wheel, motor power to the wheel, gross energy to wheels. That actually doesn't match some of the numbers on the losses, but it's because of energy flows back and forth through the battery and the generator, and that's needed to capture those. So now I'm going to skip ahead to kind of the bottom line after these, just kind of summarizing what the energy audit data means. This example is a 2030 Toyota Camry ICE. And so if you can look at the baseline transmission efficiency was 87.6%. For 2030, that improved to 91%. So that's a 26% reduction in the transmission losses. So the 26% is what we used in our modeling. Similarly, there was a 69% reduction in torque converter losses from the torque efficiency improvement from 93 to 98%. 74% reduction in pumping losses, 39 friction losses, 21 accessory losses, 5.6% increase in indicated efficiency. These are the actual indicated efficiency percentages. And so brake thermal efficiency overall improves dramatically. And that's, a lot of that is just the engine downsizing so that you don't have these poor efficiency regions that the engine operates in. So the next step is, how do we extrapolate the results to 2050. And basically what we did is we assumed that the annual pace of reductions in losses in these different categories would drop in half after 2030. So they wouldn't stop entirely, but that the rate of improvement would slow down. There were two exceptions. On the engine side, there were two exceptions to this. The first was on pumping losses. Because we already had over a 70% reduction in pumping losses even for the 2030 engine, we assumed that there would not be a lot of additional reduction after that. In other words, we want to stay away from hitting some fundamental thermodynamic limitations. And so we slowed that down to 20%. The annual rate in indicated efficiency was maintained. It was not slowed down, and that was because there is a lot of work going on right now on engine improvements, a lot of papers announcing substantial increases in indicated efficiency. So we thought that we'd be somewhat conservative on that. Even without that reduction, we wound up for the 2050 mid-range case with about a 40% indicated efficiency. In the optimistic case, 42%. We brought in a engineering consultant who said that those numbers were reasonable. I also want you to remember them because I am going to cycle back to them later. And so you can see that the bottom line, the brake thermal efficiency improved from 20.9% for the baseline to 29.6 in 2030, and then for the 2050 mid from 32.5. So still a reasonable increase from 2030 to 2050, but a much smaller increase than occurred in the next 20 years. Hybrids. Ricardo did not model a baseline hybrid. And so what we decided to do was to compare Ricardo's modeling and, of course, the energy audit data for their 2025 ICE to their 2025 hybrid. And when we did that, we found that many of the characteristics really didn't change. What we found, the ones that did change, there was an additional 80% reduction in pumping losses due to the ability to shut the engine off when it's in low load conditions. There was an additional 30% reduction in friction losses, and there was a 20% tractive energy provided by the regenerator braking system. So when you put these together, it raised the brake thermal efficiency to 33.7%. But these three numbers here are basically all we did for 2030 as far as assessing the hybrid efficiency compared to the ICE. There is a percent of waste heat recovered, which we use after 2030, and I have another slide later that will show that. Oh, okay. Now, of course, there's one other thing that we had to do, and that is assess the efficiency of the electric motors and generators and of the battery pack. And so that's this table down on the bottom. We found from the energy audit data that there did not appear to be a lot of difference in the efficiency being used as a generator motor, but there was a little bit, and so we did include that. And then the battery efficiency, even in the baseline, was very, very high. And so these assessments of efficiency improvements were done independently from the Ricardo. There's one case we did not use the Ricardo data to assess the 2050 impacts. But again, the improvements from 2030 to 2050 are modest. I'll also point out that these generator, motor, and battery efficiencies were also used for plug-in hybrids and battery electrics and fuel cell vehicles. Vehicle loads. Ricardo did not model any changes in vehicle load, so we had to do this separately. We did use the Ricardo baseline tractive loads. So we started from the exact same point as we did for the other assessments. And this is just a list of what we started with. For tire and rolling resistance, our future projections were based largely upon a graph that Michelin used to have posted on their website, which shows the progression in rolling resistance of their best rolling resistance tires from 1980 to 2010. And if you actually crank the numbers and compute an annual rate, it comes out to just about exactly a 2% annual reduction per year. And so for the mid-range case, we cut that to 1.5% annual reduction. For the optimistic case, we left it at 2%. In both cases after 2030, we dropped it to 1% annual reduction. So again, assuming that improvements would continue, but at a slower pace than has occurred in the past. And then the ones on the bottom is just the final rolling resistance multipliers that we fed into our energy model. Drag projections were done by assessing announcements from manufacturers, assessing research papers. And so there were two aspects of this. One is to look at the coefficient of drag reduction improvement. For the mid-range case, it was 15% in 2030, 25% in 2050. We also looked at frontal area reductions. This is cases in which the vehicles, one example, the vehicle will decrease its ride height on the highway. And so we for the 2050 mid-range and the 2030 optimistic, we assumed there'd be some reduction, and in the optimistic case, a 10% reduction. So again, the numbers on the bottom here are just the first one is the coefficient of drag applied to these 6 different vehicles that we had in our report. You can see that the sport utilities and the minivans and the pickup trucks still, their higher coefficient of drag is maintained. Everything's reduced proportionally. And then these are the final multipliers that were fed into the energy model. Weight reduction. Again, this was done based upon recent papers of the potential of reducing weight from high-strength steel and aluminum primarily, also magnesium. We did not use carbon fiber. Our assessment was that carbon fiber would always be too expensive to be used in mass market vehicles. So even for 2050, it was not used. And so the 2030 for cars and unibody, 25% weight reduction. For 2050, that was up to 40%. 40% is what the studies say you can probably get with an aluminum intensive structure and secondary weight reduction. We cut down the number that we actually used in our model for the mid-range case. This is an acknowledgement that vehicle weight has grown in the past due to things like features and safety and performance, and that some additional weight growth would likely occur in the future. So this is 25% was cut to 20% in the mid-range case. For the optimistic case, we did not cut it down. Body and frame trucks were assumed to be able to achieve only 80% of the weight reduction that you could on cars and unibody due to the constraint of having the tow. And then the cost is simply right out of the 2017 to 25 light-duty vehicle standard rulemaking. Okay, the energy balance model, I'm not going to say much about this. It's a pretty standard energy balance model. For the gearheads, these are the basic equations that Dan Mesler used for his modeling. The losses that he incorporated into the model, these are very similar to the list I talked about before, the outputs from EPA's energy audit model. Some additional things have to be incorporated for some of the other characteristics, but it's very similar to that. He benchmarked the model. So for the first column here is the target CAFE that came from the testing of the vehicles, and then this is the results that came out of Mesler's model after he input these factors. And they're pretty close. One case where the highway was off somewhat compared to the official CAFE test value, but this is good correlation for this kind of work. Okay, now I'm going to talk about the results of this. And this is the table I showed before for the Camry, except that now I've expanded it to include the load changes on the bottom. So, so percent reduction in coefficient of drag here, tire rolling resistance here, weight here. So now when you put all these things together, these are the fuel economies that you come up with. And for 2030 mid-range case, the fuel economy approximately doubles from the baseline. 2050 mid-range, you get another 30% or so increase in it. The optimistic case is considerably higher yet. So these are some pretty shocking numbers, but they're all a result of consistently and carefully incorporating all of the different technology advances in all the different areas. Now here again, it's this is the Camry hybrid where you're adding on the additional. You see the percent tractive energy provided by the regen goes up a little bit over time. This has to do with the higher efficiencies in the electric motors and in the battery pack. And the other thing that we added in the long run is some waste heat recovery. We only did this for hybrids because we assumed that waste heat recovery would need the energy storage system that hybrids had to be effective. And in 2050 mid-range case, we assumed that 1% of the waste heat, about 60% of the energy from gasoline goes out as waste heat. So about 1% gets recaptured and fed back into the system. In an optimistic case, it goes to 2%. And so now with the hybrid systems, the 2030 mid-range for the Camry is about 82 miles per gallon. The 2050 mid-range, 116. The optimistic goes up to 150. And the hybrid benefits over the conventional goes up a little more bit, even though the actual amount of additional fuel consumption reduction goes down. And here's the summary slide for ICEs and hybrids. So on the y-axis is fuel consumption. On the second y-axis is fuel economy. They're just the inverse of each other. And this is by year. Green is the historical. We saw a big reduction in the 70s and early 80s. It was flat for a long time. And now we're starting back down again. So the blue line here is the internal combustion engine mid-range. The green line is the internal combustion engine optimistic. The orange is the hybrid mid-range, and the red is the hybrid optimistic. And so you can see, and I've also posted on here the actual CAFE standards for 2016 and for 2025. These are the purple. So you can see that the committee's estimates show that the CAFE standards can probably be met with these weight reductions and improvements in the ICE. The reason why EPA had hybrids is because they had less weight reduction in their model and their assessments than we included in ours. But if you look at the hybrid mid-range case, by 2050, you're up to 95 miles per gallon, and that's for cars plus light trucks combined. If you look at cars only, it's about 112 miles per gallon. Battery electric fuel cell vehicles, these of course had to be done completely independently. We did apply all the same reduction assumptions about load reduction to them. The first table is the fuel cell efficiency projections for mid-range and optimistic case. These are rather conservative. We've seen projections by other people that say that the fuel cell can do better than that. The theoretical limit is over 80%. But we assume that much of the improvements in fuel cells in the future would be devoted to cost reduction, and therefore that the efficiency may not improve quite as much as that. The table on the bottom is all the generator, motor, and battery efficiencies. These are identical to what we used for the hybrid case. And so if you look at the overall MPG results, and I should mention that, of course, for the battery electric, this table at the bottom is all that really matters. All you have is generator, motor, and battery efficiencies. And so now if you look at the results, and I've highlighted the 2050 mid-range. This is miles per gallon gasoline equivalent, cars and light trucks. So so for cars alone, it's 87. For light trucks, it's 61. The average is about 75. The hybrids, 112 cars, 77 truck, average is about 95. And the battery electrics and the fuel cell vehicles are much, much higher yet. For plug-in hybrids, we simply assume that the efficiency would be the same as a battery electric during charge depleting mode and the same as the hybrid during charge sustaining mode. Okay, now let's turn attention to the cost estimates. This is a little hard to follow. Let me start with the load reduction. That fed in directly both into the cost, but also fed into the energy balance model. And so, as I said before, the energy balance model outputs vehicle efficiency. The vehicle efficiency directly affects the cost of the battery and the cost of the hydrogen tank. Those are both related to how efficient the vehicle is. The balance model also put out power, and these directly affect the engine cost, the fuel cell cost, and the electric motor cost, all of which are sized to the power capacity of the vehicle. Now, of all the costs that we did, the ICE costs are the least accurate or the least well done. And this is because, for two reasons. One is that we were looking at transitions. And when you're looking at transitions, what really matters is what's the incremental cost of the transmissions compared to the baseline. So what the baseline cost is not as important. And the other problem we had is that we really don't know what technology it's going to be. Because we did the assessments in terms of losses and efficiencies, it's very unclear what the technology is going to be. So we simply fed in some estimates from MIT series of reports in 2007 as the basis for the ICE cost. From there, we very carefully assessed the change in cost. The hybrid cost was the ICE cost plus the cost of the battery pack, the motor, all the different hybrid system costs. Then you get an energy credit for a smaller engine and a credit for eliminating the stop-start system. Next step is moving from hybrids to plug-in hybrids. You have a charger cost that you have to add, but it's mostly just assessing what's the change in the cost of the battery, the electric motor, power electronics, and the engine downsizing. So all the other costs were assumed to be the same, including the hybrid system costs were assumed to be the same for the plug-in hybrid. From the plug-in hybrid, you move to the battery electric, which again, more assessment of the change in the cost of the battery and the motors. Now, and you also get to completely delete the engine, which is a big credit. And then for fuel cells, it's similar to the battery electric, except of course you have to assess the cost of the fuel cell stack and the hydrogen storage tank. So this is an overview of how we went about assessing the cost. All costs assumed high volume production. So even the costs you see here, for example, battery electric vehicles and fuel cell vehicles, this is what we assume they would cost in high volume today. So these are not numbers that you're normally used to looking at. Our modeling group added in the additional costs that would happen if you were still in low volume production, but that we were asked specifically to provide only high volume cost estimates. I already talked about the ICE cost. Okay, let's go on. Powertrain sizing. Motor sizes. So the electric motor. For a hybrid, we use 20%, electric motor 20% the size of the total propulsion power needed for the vehicle. For plug-in hybrids, we use 60%. We did have a 90% estimate for an extended range plug-in hybrid, but we actually did not, we wound up not using that. And of course, for battery electric fuel cells, it's 100%. Engine size, we assume that the hybrids could be downsized by 15%, plug-in hybrids by 20%. And we also had a factor for compressed natural gas vehicles where to maintain performance, you actually have to increase the size of the engine by 10%. Note that we did not use any engine downsizing on body and frame. The assumption was that body and frame vehicles needed to maintain their towing capacity, and the battery would eventually deplete, and so you could not downsize the engine on these. And then our assumptions were that cars were 100% unibody and light trucks were 60% unibody. And then same thing for fuel cell systems, that the fuel cell stack would be 80% of the total propulsion power needed for unibodies and 100% for body and frames. I have a bunch of detailed cost charts. I'm not going to go through these. I just want to show you how the costs were assessed. Downsized engine credits, we actually had 5 different types of potential credits. One is for the load reduction. Another was for hybrids, plug-in hybrids, compressed natural gas vehicles. That's actually a cost increase. And compressed natural gas with HEVs. And the ICE credit was derived from some FEV teardown work, where they actually looked at what the cost savings would be for reducing the size of the engine. And this includes both just downsizing the same number of cylinders and downsizing while reducing the number of cylinders. And so we wound up using $171 times the percent power reduction times the number of cylinders on the vehicle. The other major credit is, of course, if you eliminated the engine for battery electric and fuel cell vehicles, $4,000 credit for cars and $5,000 credit for light trucks. Load reduction costs. Again, the material cost came directly out of the federal rulemaking. It was a sliding scale based upon how much weight reduction you did. And then I discussed how much weight reduction there was. So this is just simply a multiplicative exercise here. Body and frame, we used a little different estimate. Aerodynamic reductions, we assume that the full aerodynamic reduction would be $200 and would phase in over time. And tire rolling resistance would be $50. Battery sizing inputs. The range. One important point to note is that we did not increase the range of battery electrics over time. Instead, improvements were all taken out in cost reductions. So this is the range on the test cycles, which means that the range in the real world would be 20% less than this. For battery electrics, we assumed the 100-mile real-world range, added 20% for the test cycles, added another 10 miles as a reserve. Fuel cell vehicles need a larger battery pack than conventional hybrids because they need to partially run on the battery while the fuel cell warms up. And compressed natural gas vehicles, we again use the 300-mile real-world range. We assumed the battery deterioration factor, which also increased the size of the battery pack so that the range did not deteriorate too much in use. Battery depth of discharge has a major impact on the size of the battery pack. This improves over time. Hybrid batteries were not sized on the basis of kilowatt hours. Instead, they were sized on the basis of power, kilowatts. And the power capability of the hybrid batteries assumed to increase over time. And so that's what these numbers here are. And then finally, the fuel cell stack efficiencies, which you've seen before. Battery and motor costs. The battery costs, let's talk about 2030. They're very different depending upon the size of the battery pack. So your battery electric is going to have the lowest cost per kilowatt hour because the large battery pack means that they don't need high power cells. As you go to smaller battery packs, the cost per kilowatt hour goes up to provide the power that's needed. So $250 in 2030, $160 in 2050. These are the mid-range case. These are right in line with other assessments we've seen of future battery costs. And what we've seen is that the raw materials alone in a lithium-ion battery are probably somewhere in the $80 to $100 per kilowatt hour range. So chances are you really can't get too much below 160 or 150. Assess the cost for the onboard converter to recharge. The battery motor costs, I'm not going to go into those except to note that most people in the past have assessed have assessed motor costs only on the basis of dollars per kilowatt. When we looked through FEV teardown analysis of batteries and their supporting components, we found that there's actually a large fixed cost that doesn't really vary based on the size of the electric motor. Of course, that will still go down over time with learning, but we did split this into fixed and variable costs. Hybrid system costs. In the red box here, these are the different types of systems that you need to add to a hybrid vehicle. And include things like coordinated braking. Do you need to make some changes to the body to accommodate the components? You get credits for alternators and service battery eliminations. You need to work on an electric air conditioning compressor. You have heating, and inverter and distribution requirements. So fortunately, just before this project was complete, FEV did a teardown assessment of all these components. The nice thing about it is that we know that they captured all the components. And this is the first time that I'm aware of that anyone has been able to do a study that captured all the components. So we used these results. These are from Europe, but we converted them to the U.S. This is just a chart of how we changed them over time. Again, I'm not going to go through this. We'll note that we applied learning to these, and that in a couple cases we applied some step functions. And the reason for this is that we had good information that there were better brake coordinating systems coming. So in 2020, we cut the cost in half. Kind of arbitrary when it occurs, but it has to occur sometime. Electric air conditioning compressor, the assumption was that as hybrids come high volume, that the air conditioning compressor would be driven off the electric motor, and you would eliminate the need for a separate compressor. So, and then finally, there can be some improvements in the long run by integrating the electric motor inside the transmission, reducing the cost of the transmission as well. Fuel cell stack and tank costs. The fuel cell stacks are in dollars per kilowatt hours. These are, we think, reasonable, and these were vetted by quite a few people working on fuel cells outside the committee. The fuel cell tank costs were, again, divided into fixed and variable costs depending on how much is stored. We also did costs for CNG tanks, and they were quite a bit lower because the pressures for CNG are quite a bit lower. Load reduction. You have the direct cost of the load reduction. You have a credit for the ICE downsized that directly goes along with that. These are the ICE technology costs that we derive from the MIT work, plus the turbocharging cost. We added a stop-start system cost, and then for hybrids only, in the long run, a waste heat recovery cost. This is the exact same chart, except for light trucks. Again, I'll just let people look at this in the handouts afterwards if you're interested. Okay, the interesting stuff. This is a summary chart where we put the incremental cost. This is not the total cost of the vehicle. This is the cost over the baseline ICE. It's direct manufacturing costs. It does not include any kind of retail price markup. The interesting thing here is that in the long run, around 2040, these costs converge, where the battery electric and the fuel cell vehicle costs cross the hybrid costs. And in fact, by 2045, they're crossing the ICE costs. So this is something that is new and relatively unexpected. It's a function not just of the improvements expected in the battery packs and the fuel cell stacks, but also because we carefully modeled the load reduction impacts. And load reductions have a direct impact on the size and cost of the fuel cell stack and the battery pack. One other important point, plug-in hybrids always have a substantial premium. All right. So this is the same slide except for light trucks. The costs are higher, of course, the incremental costs, but and it takes a little longer for them to cross, but the same general characteristics. If you look at optimistic costs, now they're crossing around 2030. Now, they probably can't get to high volume production by 2030. So again, if you add the markups for lower volume production, there's still going to be a premium. But it does show that they, in an optimistic case, in the long run, they could be considerably cheaper than an ICE engine. It's something I pushed back on a lot when I first heard about it. And the answer that I got back, at least for the fuel cell stack, was that the raw materials in the fuel cell are actually quite inexpensive. It's only the precious metal loadings, and those are expected to be well below 10 grams by this period. At $50 per gram, that's less than $500. So it does seem to potentially make a certain amount of sense and some validation of these numbers. Again, a light truck's optimistic case, a little behind the cars, but still cross. So the last point I want to leave you with is that the results of these modelings is likely conservative. We pushed back the Ricardo 2020 to 25 results to 2030 for the mid-range case. We assumed a substantial reduction in the rate of improvement after 2030. We only considered turbo compounding for waste heat recovery, and that only after 2030. There are other methods that have potentially higher efficiency. We did not consider any new ICE combustion techniques. We did not consider carbon fiber. We did not consider batteries beyond lithium ion. The fuel cell efficiency gains were much less than theoretically possible. We did not consider off-cycle improvements. And there were some new lightweight material cost studies that came out towards the end of our project that had significantly lower cost than the EPA work did, or numbers that went into the 2025 did, and we did not incorporate those as well. So I have some slides here, just some examples of the way things have been improving recently, but in the interest of time, I'll skip those. And so the key message is there's a lot more running room for conventional technologies than we think. Battery electric fuel cell vehicles will be cost competitive in the long term. So the barriers for these are likely not going to be on the vehicle side. For battery electrics, it will be with the long recharge times and the short range. And for fuel cells, it's of course, where do you get the hydrogen and how do you create the infrastructure? Fuel cells will always command a significant cost premium, and as your baseline, and I'm sorry, as your ICEs and your hybrids improve, their incremental fuel savings will diminish, not necessarily a real good business case in the long run. And then, of course, if any of these fundamental technology breakthroughs occur that we did not consider, they would further increase the efficiency and reduce costs. So that's it for my canned speech, and we can go back to taking questions.
Thank you, John. John maybe took a little longer than we expected at the beginning, but we always also planned this webinar to go for about 90 minutes and not an hour. So we got considerable amount of time to discussion as long as people can stay. The presentation will be available afterwards on the web and sort of the recording and all of that. So that is possible. So this is a time if you wanted to ask your questions either verbally or just raise your hand or type in your questions. While people are raising their questions, I do see a question that's already come in from Alan Schaefer. And Alan, I'll just unmute you and you can just ask your questions, even though you sort of typed in. And obviously, it's a question about diesels. Alan, go ahead.
Can you hear me?
Sure, yeah.
You can hear me? Okay. As I noted in the question there, I'm curious about the decision that diesels were excluded from this analysis, given that the National Petroleum Council and others see a growing role for diesel going into the out years that are within the scope of the NAS study, that half of the cars sold in Europe over the last decade have been powered by diesels, and a growing number of choices are available in the U.S. that are powered by diesel. What was the basis for excluding diesel from the beginning? And given all that, are there any feelings that we may have missed an opportunity here to model a technology that itself could be getting better efficiencies and hybridization that could get into those 80 and 90 MPGs like you're showing for the the gasoline hybrids?
Yes. There was a long sidebar in the NAS report discussing diesels and why they were excluded. I mean, the first comment I'll make as far as the European experience goes, a lot of that's being driven by the fact that diesel fuel in Europe is taxed differentially and is much cheaper than gasoline. So a lot of people are buying diesels just to get to the cheaper fuel. But that's not the reason that we did not consider them. The primary reason is that right now diesels have a far higher level of technology on them than gasoline vehicles do. Turbocharging, direct injection, high pressure injection, cooled EGR, all these things, as they get applied to the gasoline engine, the gap in efficiency between the gasoline and the diesel is going to narrow considerably. So that was one of the major points. Another point is that when you start looking at what might happen after 2030, we're not even sure what kind of combustion an engine will run. Compression ratios in diesel engines are coming down. Compression ratios in gasoline engines are going up. There's a lot of work being done on homogeneous charge compression ignition, which will make the gasoline engine run like a diesel. And so it just was very unclear to us how we would even differentiate gasoline and diesel engines in the long run. And finally, the last point is simply that when you start looking at what the potential differences might be in the long run, they're very small compared to all the other factors that we're considering with load reductions and battery electrics and fuel cells and all these things. And it was just felt that it would not add significantly to the analysis and would introduce a considerable additional complication. So right or wrong, those are the reasons that we did not separately model a diesel engine.
John, at the beginning, you mentioned a little bit about why natural gas vehicles weren't considered in a bit of detail, had to do with upstream emissions and the leakage, and etc. Part of the question that's come in is about whether, if you had more condensates, the natural gas condensates fraction increasing, the committee overall, the fuel side of it, consider the contribution from condensates as transportation fuels and what impact, if any, you saw?
Well, okay, the fuel subcommittee did a lot of work on natural gas. And there's a lot of information about their assessments in the report. It didn't really affect the vehicle committee much. The efficiency running on natural gas is virtually unchanged compared to running on gasoline. And so the assumption was that the efficiencies would be the same. We did do some cost assessments on natural gas that were shown in some of the slides, as far as needing a little bigger engine, needing your natural gas storage tank. But that's basically all we did on the vehicle side, and then we just passed these things along to the modeling group, which integrated all the information from the fuels group. So sorry, I can't be more helpful.
The next question comes from Lou Fulton. Lou, you're unmuted, so go ahead.
Hi, thanks, Anup, and thank you, John. That was really interesting. I may have missed it, but I'd like to ask you about the assumptions on high volume production and how you get to high volume production. Did you folks assume any learning? Was there a cumulative production aspect to cost reduction, or was it simply that the minute you get to high volume production, you get those costs?
Right, okay. Unfortunately, the way that the committee broke this up makes it a little harder to understand because we had two different types of learning that we incorporated. One was just kind of a general technological based learning that people figure out better ways of doing things. My current favorite example is the 6-speed automatic transmission, which has pretty much the same number of clutches and gears as the old 4-speed did. Therefore, it's the same cost. They've just figured out clever ways to get more gear paths out of the same number of components. So so we generally used about 1% for that type of learning. The second type of learning is through volume. That was done entirely by the modeling group. So, and so that was not incorporated in the numbers that I showed you at all. So yeah, they asked us to assess high volume production. We didn't assign a number to that high volume production, but to us it meant that you're running your facilities full out. You know, your R&D costs are covered. You could run factories at their maximum efficiency. So we just didn't worry about any of that stuff, and just purely looked at what the ultimate cost would be of the technology. Now the modeling group did go through and did a lot of assessments for how to add on all these other costs. And in the early years with low volume production, their costs were far, far higher than the cost that we gave them. And then with learning and the other factors, they would come down over time. I hope I answered your question.
John, the next question comes from Dominic Chico, and it's kind of about asking you about, hey, how much improvement in internal combustion engine is necessary to achieve continued existence or to be relevant? Or in your opinion, what role does the internal combustion engine play in the future as other technologies keep on improving?
Right. Well, I mean, based on the results that we have here, I think the IC clearly has a lot more room to grow than people think. Yeah, and the indicated efficiency is one example of that. We used, for 2050, we used 40% for the mid-range case and 42% for the optimistic case. Well, PSA has already announced they're going to go into production in 2018 with a dedicated EGR engine. And this is one where you feed back one of the exhausts from one of the cylinders, four-cylinder, back into the intakes, 25% EGR. They take the dedicated cylinder, they run it rich to create hydrogen to help with the combustion process. And Terry Alger of the Hedge Consortium says that this engine will be over 42% indicated efficiency. So, I mean, so it's already at what we said 2050 optimistic. So I do think IC has a long way to go, a lot of improvements that can still happen on it. And it's a two-edged sword. The good news is that we will see far more improvements far more rapidly than we ever thought. The bad news is it's going to make it harder to make the transition. So did I answer your question, John?
Yeah. That question had come from Dominic Ford.
Sorry, Dominic. Sorry, Dominic.
The next question is a short clarification from Harry Sigworth of Chevron. The question is, what did you assume for the range of the fuel cell?
Oh, yeah, sorry. That was actually on one of the sheets I showed you, but I didn't highlight it. It was 300-mile real-world range, which meant 390 miles on the test cycles.
Well, at this stage, there aren't any. Oh, well, there is. I think Dominic has a follow-on, and I should have just maybe unmuted him. So Dominic, could you ask your follow-up and go ahead?
Am I? Oh, there might be some feedback.
Okay, I'm sorry, I just kind of muted you, and I'm going to just read out your question. And the question is on the fuel cell and natural gas side. What's the likelihood that the U.S. can make a significant change in the infrastructure side? Because these are gaseous fuels, both hydrogen, natural gas, and how does that transition to refueling infrastructure for gaseous fuels take place? What did the committee think on that front?
Right. Well, again, the fuel subcommittee really handled all those issues. So all I can venture there is kind of my personal opinion. If you look at the fuel cell vehicle from the vehicle only, it looks like a slam dunk. You're talking about a vehicle that has the range of a conventional vehicle, the refueling time of a conventional vehicle. It's more efficient. In the long run, it should be cheaper. It's quieter. Because it has electric motor, it has better drivability, better low-end torque. You can do better packaging within the vehicle because the components don't have to be oriented in a particular order. I mean, what's not to like? Yeah, it's a wonderful step forward. The problem, of course, is where do you get the hydrogen from? I'm not as concerned about the infrastructure. It would take a long time, but we have historical examples of ways that people have switched infrastructure. And, we've built our whole natural gas system for delivering natural gas to homes for heating. But I tend to be much more concerned about where do you get the hydrogen from, and can you create it in a competitive way.
Okay. At this stage, I don't see any additional questions, and we'll take a short pause if anybody wants to ask any more questions before we kind of close out. Just for everybody's information, I think we repeated it. The webinar slides and everything would be available on the website, so do please check that. To those who did say that you would want to be added to our ICCT mailing list, we will do that in a short while of time. It's not a very high volume mailing list, so, but every now and then you might expect an email on that list if you said yes to it. So let me just wait if there is any other final questions, or John, if you wanted to sort of make any final comments that you kind of make during the course of presentation.
Yeah. Well, I mean, the one comment I will make is that the truly transformational technology out there is actually computers. It's computer-aided design, computer simulations, onboard computer controls. This is why all of these technologies are happening. This is why the ICE is still going to improve so much. But it also opens the doors to alternatives as well. But I think most people are underestimating the impact of computer simulations and stuff. Lightweight materials are a great example. In the past, it was never really possible to figure out how to optimize each of the components on a vehicle. You reduce the weight on something, but you really wouldn't know what the impact would be on noise and vibration and safety until you actually went out and built a model, which is really, really slow, expensive, and inefficient. And so the computer models are getting close to the stage where manufacturers will be able to optimize the material, the size, and just the shape of every piece on the vehicle simultaneously. And that's just going to revolutionize weight reduction.
Okay, since there are no further outstanding questions at this time, we should be able to close. Thank you everybody for attending, and thanks John for taking the time to put this together. If you do have additional questions you would like to send us by email, feel free to do so, and look forward to the presentation on the website. Thanks again, and goodbye.